Hi, Emma. Emma, can you hear me? You may have
Oh
to,
yeah.
yeah, you have to unmute your microphone when you first log on anymore. The change the GoToMeeting made, which I'm not real happy with, but they made it
Oh really?
because they have some meetings where they have like 1,000 participants. And if they don't
Hmm.
mute everybody, then everybody starts talking at once and nobody can hear anything.
Right.
But it doesn't particularly work well for tutors with one student. Because you have to make sure you unmute it when you go in. All right, what do we got? Did you send me anything, or can you verbalize?
I think I can, yeah, verbalize it all.
Okay, let me widen my screen here. What do we got for starters?
Okay, so we started limits of infinity today.
Okay.
And so I have use graphs and tables to find limit x is going to infinity f of x and limit x is going to negative infinity f of x, and identify all horizontal asymptotes. And the first one is cosine, and then in parentheses 1 over x.
All right. Let's draw the curve. Hold on. Do we need to use a graph on this? What
It
happens?
says use graphs and tables.
I know, but what happens to 1 over x as x goes to infinity? What's 1 over x do?
Well, you would
It
put
goes
infinity
to 0.
for x.
It goes to 0.
Oh.
Okay? In other words,
Okay.
this term right here, if the denominator is going to infinity and the numerator is staying at a number, then the whole thing is approaching 0.
Okay.
Okay? Now, the graph of this thing, if you used a table when x is equal to 1, the cosine of 1 is 0. Well, no, that we're going to be in radians. But there's no question that what's inside the parentheses goes to 0. And what's the cosine of 0?
1.
Yeah. In other words, the cosine curve looks like this. So if the argument is going to 0, then the cosine's going to 1. Now, if they wanted you to use graphs, then let's graph this thing also. Let me do that real quick. On Wolfram Alpha. And it's also worth noting what horizontal asymptotes are. They're the end behavior. That's what the function's going to approach as x goes to infinity or negative infinity.
Okay.
All right, notice how strange the graph looks. And this is zoomed in, that's zoomed out.
Okay.
And it's actually fairly tough to see what happens as x goes to infinity because they don't, well, you can kind of see it in the bottom one. In other words, here, let me draw, or let me put a horizontal asymptote on it right there at 1. Okay? You can see that the function is approaching that horizontal asymptote as I go all the way to the right and also all the way to the left. In other words, as the x goes to negative infinity, it also is the cosine of 0. So it's going to go to 1 whether it's positive infinity or negative infinity, and that makes an asymptote at 1. In other words, if I went out to this one that's zoomed in, there's an asymptote right there. That this part of the function is going to approach as you go further and further to the right or further and further to the left.
Okay.
Okay. Let's not put that away for the moment. What else?
Okay. So f of x is sine 2x. All over x.
As x goes to infinity or 0?
Yes. Infinity.
Okay. The numerator is oscillating like that. Whether it's 2x or x doesn't matter. The numerator goes up and down. So as we go further and further to the right, the numerator bounces back and forth between +1 and -1. But the denominator keeps getting bigger and bigger and bigger and bigger. So this whole thing is going to go to 0 for the same reason the cosine of 1 over x went to 0. If your denominator blows up and your numerator does not, either bounces between two very finite numbers or doesn't do anything else, then this whole thing is going to 0. And the sign of 0? Well, no, I'm sorry, I put that incorrectly. If this is going to infinity and this is not, then the whole thing has to go to 0 again.
Okay.
Okay. Let's graph that on my Wolfram alpha just to show you. Sine 2x over x, is that correct?
Yes.
The beauty of Wolfram alpha is it tells you what you put in. Again, on this scale here, you can't really see what's going on at infinity. But if I look at the bottom scale, you can see that the amplitude gets smaller and smaller and smaller, right?
Right.
So as I go further and further to the right, it's pretty clear that this thing approaches a horizontal asymptote at 0, y equals 0.
Okay.
Same thing to the left. So whether it's positive infinity or negative infinity, it's approaching 0. The graph, I only needed to verify it. In other words, I didn't really need the graph to figure out the answer. So all I needed was to realize that the denominator is blowing up and the numerator is bouncing back and forth. All right, what else?
Okay. So I have limit of 1 over x minus 2, and x is going to positive 2.
If you do direct substitution, what do you get?
1 over, well, 1.
1 over 0, not 1.
Oh, yeah.
There's a big difference. If your denominator is 0 and your numerator is any number at all, then the limit of that thing is infinity. They may choose to call it undefined if they don't like using the word infinity. But even if I had 1,000 over 0, that's infinity. Even if I have 0.0001 over 0, that's infinity. If the denominator, and notice if you try some numbers there, if you put in 0.1 for the denominator, you'll get 10. Put in 0.01, you'll get 100. Put in 0.0001, you'll get 1,000. In other words, the closer this denominator gets to 0, the bigger the answer gets.
Okay.
So I can tell this thing goes to infinity without graphing it.
Okay.
Okay? But if we were to graph that, that's a hyperbolic function. That's kind of like 1 over x. And
Okay.
you know how hyperbolic functions graph. They look like this.
Right.
And as we go to positive 2, we're going to head towards infinity, the limit of that.
Okay. So one of them is it's approaching 2 from the right side, and then one is just it's approaching 2. So what's the difference between that?
Okay. If I'm approaching 2 from the right side, then this number is positive, right? Because I always have 2 plus something minus 2. So this number might start out at 0.01, and then it's going to get 0.001, and then it's going to get 0.0001, the closer and closer I get to 2. So the limit is definitely infinity, because the thing gets bigger and bigger and bigger the closer you get to 2.
Right.
Now, if I approach 2 from the left side, let's talk about that for a moment. Well, now I've got 1 over, well, when I'm, now the first number is minus 0.01. The next one is minus 0.001, and then minus 0.0001. In other words, when we approach it from the left side, let's say the first number we plug in is 1.9. Well, that gives you a negative denominator. And even though that denominator gets closer and closer to 0 as we move towards 2, it stays negative. So the limit of that as we approach from the negative side is negative infinity.
Okay.
Which means the limit as x approaches 2 is what?
So
if it's infinity when we approach from the right, and it's negative infinity when we approach from the left.
So it doesn't exist, because they're not the same?
Exactly. And if they are not identical, it does not exist.
Okay.
That's one of the easier problems in limits, is if you do not get the same thing from the left or the right, it does not exist. And a classic example of this would be y equal 1 over x, which is just a slight alteration of the one we looked at, but this is a little bit easier to see.
Okay.
Notice that as we go to the right, as x goes to positive infinity, we're approaching 0. Ooh. Well, we're not going to infinity. We're going to 2, right?
Right.
So the equivalent would be as x approaches 0.
Okay.
Now, as x approaches 0 from the right, this thing's headed up to positive infinity, right?
Right.
And as x approaches 0 from the left, it's headed towards negative infinity.
Okay.
So the limit of this function as x approaches 0 would not exist.
Okay.
Okay? Now, just for the heck of it, I'm going to show you an interesting thing here. If I plot 1 over x squared, I get this. Now, as x approaches 0 from the left, positive infinity, as x approaches 0 from the right, positive infinity. So does the limit exist at x as x approaches 0? Yes,
Yes.
it does exist. As to what it is, some books would have a problem saying it's infinity because they don't like giving that as an answer because it sounds like a number. So they might still choose to say that that limit is undefined. You basically have three words. You have undefined, you have does not exist, and you have infinity. And they really are not the same, even though a lot of people tend to use them interchangeably. Does not exist means does not exist. That does not mean infinity. Okay? Undefined can be infinity because they wouldn't want to use the word infinity. Undefined kind of means the same as infinity in some courses. Not all. Some mathematicians don't have any problem using the word infinity. I would prefer to say the limit of that is plus infinity. Okay, rather than undefined, just because there is a slight difference in meaning.
Right.
All right, what else you got?
Okay, so find limit x is going to positive infinity y and limit x is going to negative infinity y of y equals, in parentheses, 2 minus x over x plus 1, and then another set of parentheses, x squared over x plus x squared.
Like that?
Yes.
When you say x goes to...
Oh, the bottom one on the right is actually 5 plus x squared. I was looking at the wrong one.
Okay. Don't think it's going to matter as to which one you gave. When you talk about x going to infinity, you're talking about horizontal asymptotes. Well, if I gave you that function right there, where is the horizontal asymptote?
Just at 0?
No, it's, you take the highest degree, if the degree of the numerator and the denominator is the same, which it is, it's x there and x there, then you take the ratio of those coefficients, which in this case is minus 1. In other words, I don't care about the 2, I don't care about the 1, I don't care about this 5 over here. That's why I said it's not going to matter.
Okay.
If I'm letting x go to infinity, the only term I care about in numerator and denominator is the highest degree of the variable.
Okay.
So the one on the left goes to minus 1. What's the one on the right go to?
Just 1?
Just 1. So their product is minus 1. So that limit is minus 1.
Oh, okay. So you just ignore all the real numbers and use the x's?
Yes, it's the same as if I told you this. If I say what is the limit of that function as x goes to infinity, the only thing I care about is that, the ratio of 4 to 2.
Okay.
All of these I can forget. When you're talking end behavior, the only term that matters is the highest degree. Everyone else you can ignore. Now, it's only the ratio of these two if these powers are the same. In other words, if that was an x squared and this is an x cubed, well, clearly the bottom is blowing up before the top does. So that would be going to 0.
Okay.
And if this were x to the 4th and this were x cubed, well, now the top is blowing up. Right? X 4th over x cubed is x. It's in the numerator. As x goes to infinity, the whole thing goes to infinity.
Okay.
So this ratio of the coefficients is only true if the degree of the variable is the same. In this term on the left, it's 1 there and it's 1 there. And in the term on the right, it's 2 there and it's 2 there. And even if you'd have given that wrong, it wouldn't affect anything. The only thing I care about is that x squared over x squared.
Okay.
Okay?
So I have one, and it's so 2 over x plus 1 in parentheses, and then in another set 5x squared minus 1 over x squared. But the 2x is like separate from the 1, so it would be 2 over x plus 1.
Okay.
Yeah. Yeah.
And we're letting x go to infinity?
Yes, yeah.
Okay. What's the left side? The left parentheses. What happens to that quantity as x goes to infinity?
Well, it's not. Is it to the same degree? Because there's no x's in the...
No? The bottom clearly blows up on that, right?
Yeah.
So what does that term go to?
Just,
When your denominator blows up and your numerator does not, the whole thing's going to 0.
0, okay.
If your numerator's blowing up and your denominator's not, the whole thing's going to infinity.
Okay.
Okay? So the only problem really comes when you have 0 over 0, which we haven't really gotten to yet, or we maybe touched upon those last session. But
yeah.
This thing's going to 0 as x goes to infinity, which means this is going to what?
So that's going to 0?
No, I'm adding 1 to 0.
Oh, to 1.
That doesn't do anything. That stays at plus 1.
Okay.
So this goes 0 plus 1, which is 1.
Mm-hmm.
And what does this go to?
Just 1. Or minus 1, so that would be 0.
No. Here we have the same degree in the numerator as we have in the denominator, which means the limit goes to the ratio of their coefficients. 5.
Okay.
Okay? Always look for that. In other words, if the numerator is bigger than the denominator, then the numerator is blowing up and it's going to plus infinity.
Okay.
If the denominator is bigger than the numerator, and by bigger I mean its degree, not its coefficient, but if the denominator was x cubed, well then it's going faster than the numerator, and that's going to 0. So it makes a big difference whether it's x cubed or x squared. If it's x squared, it equals the highest degree in the numerator, so that limit is going to be 5 over 1. So the entire limit of the function is 5.
Okay. So you only pay attention to the numbers when they're like multiplying the x, not like the minus 1.
Exactly.
When it's just subtracting and adding.
When I'm talking end behavior, which is what you're talking about, when x goes to infinity or negative infinity, then the only term that matters is that one and that one. Whatever follows that x squared, whether it's x's or numbers, you can just basically forget about.
Okay.
A little different over here. On the left side, notice that the 2 over x goes to 0, but 0 plus 1 is 1.
Right.
All right.
Okay. So I have y equals 2x plus sine x all over x.
As x goes to infinity?
Mm-hmm.
Let's split that into two functions, which we're allowed to do, right?
Yeah.
Now we can cancel those. So this part goes to 2, no matter what x is going to.
Mm-hmm.
And this part, we've already determined, since sine of big numbers just fluctuates back and forth between 1 and -1, and the
Mm-hmm.
bottom keeps getting bigger and bigger and bigger, this whole thing's got to go to 0. So we have 2 plus 0, which is 2.
Okay. So when you're using infinity, it would be 0, but when it's just like regular notation with a real number, sine x over x equals 1, right?
No, sine x over x only equals 1 as x goes to 0.
Okay.
Okay? If I graph sine x, and that's the difference, is it's only the ratio of the coefficients if x is going to infinity. But if
Okay.
I take sine x over x as x goes to 0, well, notice
Mm-hmm.
the direct substitution gives you 0 over 0.
Right.
Those are the problems that are hard, is when it's 0 over 0. If it's
Yeah.
anything other than 0 over 0, it's easy. A number over 0 is infinity. 0 over a number is 0. So the
Okay.
only difficult limit problems are when it's 0 over 0, which this is. And they haven't taught you the math yet as to how to figure this out. This limit's actually 1. And they tell
Okay.
you to memorize it.
Yeah.
And the other one they tell you to memorize is this one. As x goes to 0, the limit of that thing, again, we have 1 minus 1, so we have 0
Mm-hmm.
over 0, but
Mm-hmm.
the limit of that thing is 0.
Okay.
And again, they tell you to memorize that. So memorize that and memorize that. And then a year and a half into calculus, they'll show you how you get those numbers.
Okay.
And that's truly the truth. In other words, they can't explain to you why this limit is 1 without more calculus.
Mm-hmm.
And yet, in order to teach you calculus, they have to start out with limits. And when you
Right.
start out with limits, you need to know what this limit is. So they kind of start you out by saying, this limit is 1, memorize it, use it.
Right.
Okay? So one kind of interesting problem is, what is this? As x goes to 0. It's not that clear how to do it.
Yeah.
The secret is to multiply top and bottom by 5.
Okay.
Now, what's the sign of 5x over 5x go to as x goes to 0?
Is that just 1?
And then 5 times 1, so that limit
5.
is 5.
Okay.
Okay? In other words, whenever you have the sign of anything over anything, with the anythings
Mm-hmm.
being the same, as anything goes to 0, that thing is going to 1. And it doesn't matter if it's 5x over 5x or x over x or whatever. If it's a
Okay.
variable over the variable, then that's going to 1. It doesn't matter. Like I said, sine of 5x over 5x is going to 1. Sine of x over x is going to 1.
Okay.
Okay.
Mm-hmm.
Emma, I got to go. I got them backed up again today.
Okay, thank you.
We're going into finals. Not this way, but talk to you next time.
Okay, sounds good.
All right, bye-bye.
Bye.